So in this video, we're going to talk about how you can relate the stress, the strain within a system to the stress, and the stress within a system to the strain. All right. So we defined, you remember from maybe material science, that you have the change in length divided by the original length of a system under stress causes is the definition of strain. So if we have a stress element, before it's applied, it's a cube. After we apply the stress along the x-axis, there'll be some strain within the x and the y directions. All right, so the original length of the element x will change, will become a little bit longer. So delta x will be a positive number. All right, while the change along the y and the z directions, delta y and delta z, will both be negative. All right, and that's due to the Poisson's effect. Okay. So we can use Hooke's law. So we can say that sigma x, all right, is going to be equal to the modulus of elasticity of our material times the strain along the x-axis. All right, and then we know that we can relate the strain due to the strain in the y and the z-axis to the strain in the x-axis using the Poisson ratio. So we say that the Poisson's ratio of a material is equal to the strain in the y direction over the strain in the x direction. All right, and we can do the same thing, and that's also equal to the strain in the z direction divided by the strain in the x direction. Right? So for a stress in the x-axis, it would create a strain in the x-axis equal to sigma x over E, and then the corresponding strains due to the stress in the x-axis would be equal to minus the Poisson's ratio times the strain in the x direction. All right, so we can repeat this process for if you had a stress applied in the y direction, what strains it would cause in the y, x, and z axes, and the same thing for the z direction. Okay, so in this class, we're often going to be talking about cases where you have either biaxial or triaxial stress. So if we draw our stress element here, we're talking about cases where you'd have sigma x, you'd have sigma y, and maybe you'd also have sigma z. Right? So, so if you combine the uniaxial stress-strain relationships that we discussed on the bottom of the last page here, right? And if you combine them all together, what you end up getting is you get an equation that you could solve for the strain in the x, the y, and the z if you know if you have the known normal stresses. So if you know sigma x, sigma y, sigma z, and you know the Poisson ratio and the modulus of elasticity of the material. All right. So if you rearrange these three equations, you can rearrange them and you can solve for the stresses if you know the strains within the material. Okay. So if you know the strains along the x, y, and the normal strains, epsilon x, epsilon y, and epsilon z, you can solve for sigma x, sigma y, and sigma z. Okay. Now you can, if you plug in, whatchamacallit, these, if you have a case where you have a plane stress, where sigma z is equal to tau yz and tau zx are all equal to 0, these equations become a little bit simpler. All right, so these equations are only applicable under plane stress. All right, and then the last thing is that if you have a change in temperature, that can cause normal strain within a material. All right, so So that normal strain is going to be proportional to the linear coefficient of thermal expansion and also the change in temperature. So, and then using these formulas here, you can calculate sigma x, sigma y, and sigma z. So that concludes this video on how you can calculate the normal strains and the normal stresses. You can calculate the normal strains from the normal stresses, and you can calculate the normal stresses from the normal strains.